Okay, recording has started, and let me take you to the practice quiz here. So the graph below is f of x. Draw f prime of x on the same grid. Okay, anybody need more time on this? Alright, so first step is we look, where is the tangent line horizontal? Wherever the tangent line is horizontal, that becomes an x-intercept of this. So it's right here, that's going to go through the y-axis, the x-axis. Now, to the right of this, the slopes are positive and getting larger and larger. To the left of it, the slopes are negative, and the more left you go, the bigger the negative number, like -6 over here, while only -1 over here. And this turns out to be, and if you had any shape that is above the x-axis on the right and below the x-axis on the left, that would be sufficient for me. But we could also tell that this looks like a second degree polynomial, a parabola. And the derivative is 1 degree less, which would be linear, would be a straight line. So my hunch is this is not only going to be above on the right and below on the left, but just be a straight line over here. Now, this is something we had done before. We were just reviewing it now. Give me a little indication of your comfort level with this, because we're going to be going more, we're going to be doing this on steroids on the next problem. So, tell me how you are with that. Alright, mixed on this. So the next one is much more difficult than that. So let me put one in between this. Let's do one more like this before we go to the next one. And I'm going to just draw this next one. I'm going to call it 1.5. And if my graph is here, you draw f prime of x on the same grid. And let me give you a minute. Alright, anybody need more time stuff? Let's go ahead. Wherever the tangent line is horizontal, that's an x-intercept. Tangent line is horizontal, x-intercept. Between here and here, between those two x-intercepts, these slopes are always negative. I'm getting the biggest slope kind of about halfway in between. That would be, and maybe it's about, I don't know, -1 or -2, maybe even -3. So, they're not so much here and then up here and like this. So, the steepest, largest negative. Now, to the left of this, they are all positive. But the more left you go, the bigger the number of the slope. The right, it's all positive. The more right you go, the bigger the number. Now this curve should have been a little more straight up. I kind of arched it. If it was a real third-degree polynomial that I had drawn, this would be a second-degree polynomial, like this. Alright, so that's the extra one to practice on that. And now let's go to the number 2. Renumber it. And we may have done 1 or 2 of these, but not very many. If the graph below is the derivative, draw the graph of the original on the same grid. So this is going in the opposite direction of what we just were doing. We started with the function and then drew its derivative. Now we're starting with the derivative and we're having to draw the original function. Now I had to give you a starting point. Remember, this is called an initial condition, because when you go from the derivative to the original, there's an infinite number of functions that are the antiderivative, because of that plus c. So an initial condition, I said f of 0 is 0. So make that as a point on this graph and then draw the original. I'm going to give you a little bit of time. Anybody need more time? Alright, we know we got to go through this point. How do I go through that point? Do I go through it horizontal? Well, if I did like this, so it had a horizontal tangent line, that would be saying that the slope is 0. But we know that when x is 0, the slope is 2. So it's rising pretty fast. Its instantaneous slope is 2, so by the time it went over 1, it would go up 2. So it's got to be going through here kind of steeply. And then the further I move to the right, the more steep the slopes are. So it keeps getting steeper and steeper as I move to the right. Okay, now let's look at this. This is a special point. We know that the x-intercepts for the derivative, that's where the original function has a horizontal tangent line, because the derivative is 0 there. Now this is getting less and less steep as I move to the left, but it has to get such that when I get here, it's horizontal tangent line, directly underneath -4. Now we're moving to the left, and these are all negative slopes going down. And the further I go to the left, the more negative they are. That's kind of like this. Alright, now this also is consistent, because we're saying that this is f, while this one was f prime. So if you take the derivative of a parabola, you get a 1 degree lower straight line. Take the antiderivative of the straight line, we get the parabola. Alright, on this one, I'm anticipating not many of you got it before I did, but tell me about your, do you get it after I explain it? Totally makes sense, still kind of confusing. You can let me know if you felt really comfortable with it and were able to even get it before I put the answer up. And then a question about other x-intercept at -8. Let's look at that. Oh yeah, probably symmetry, since it's 4 units over this way. I think that's right. That would have been a better graph if I'd have gone out to -8. Thanks for pointing that out. Alright, so am I correct that we haven't done many of this? Maybe 1 or 2 before, but there weren't like homework problems on this. Is that correct? Can anybody chime in?
Yeah, I think you're correct.
Okay. Alright, good. Alright. Now, I'm going to ask you another question. Only for x greater than or equal to 0, draw the accumulated area function a of x. Draw it on the same grid. We've been working with accumulated area functions for a little while. Draw that. But only start at 0 for the x and only do the right hand side of this. So it's just going to be a real rough estimate too of the accumulated area function. Yeah, don't want to use any geometry or anything trying to figure out areas. Just do a real rough sketch. Alright, let me have you stop. And we're going to start here. When x is 0, the area is 0. So I know this is a point right here. Would it be a good idea, as I move, as x goes to the right, I'm going to accumulate more area. So should I go to the right, kind of like this, and get more area like this? Does that look right? On one hand, to me, this looks right, because as I move to the right, I'm going to get more and more area. But I'm not accumulating area fast enough. If I start with a slope of about 0 here, actually I should be accumulating area quite a bit right away, right off the bat. Because when I move 1 unit to the right, I'm going to get more than 2 area. I should be way up here. All right. So, although this is partially correct, what I drew, I want to be starting not with an initial slope like 0, but an initial slope of pretty steep. Oops. Like this. So by the time I get over to 1, I should be above 2, because I'll have quite a bit of area that I've accumulated there. And then, as I go to the right further and further, it's going to accumulate more and more area, even faster and faster. And so that looks like, notice, I can't make this a straight line either. As I move to the right, if this was a horizontal blue line, if the blue line was horizontal, then I'd accumulate area at a steady rate and I'd be a straight line over here. But if the blue line is getting larger, then my accumulated area is really going up at a more steep rate than a straight line. Now I can go to the left of this, but we lose a little bit because with negative and negative areas and all that kind of stuff. So I'm just going to focus on the right part of this. Alright, so I had my accumulate area function here. What do you notice about this accumulated area function? Does this look familiar? Let's look back to the right hand side over here. It is the same as if you had the derivative and you needed to graph the antiderivative. If you have a function, you need to graph the accumulated area function. Accumulated area functions are antiderivatives of the original function. If we're above the x-axis and things, then you can really see this really easily. It's a little bit tricky otherwise, but the main point I want to make is accumulated area functions, antiderivatives. Get those associated. Give me a little feedback on both of these then. 2 and 3, the bigger picture on those. Is that making sense? So some of the best math that I do is when I'm away from all my instruments and like I'm taking a walk, I take my dog for walks every day, and sometimes I think about math, and I remember thinking about this topic and how I could make accumulated area functions, and I remember lots of walks thinking about accumulated area functions and antiderivatives and really getting that association down for myself, and it was very helpful. All right, let's go to number 4. Estimate the average value of f of x equals x cubed from 0 to x equals 2. And again, it's just a rough estimate. You might draw a tiny diagram, you might do whatever you want, but just get a rough estimate of the average value. Okay. By the way, on one of my hobbies is learning new math. I haven't been doing it lately. I need to get back into it. But one of the things that I found really helpful is when I've been learning something new in math is when I go take a walk, I try to summarize. All right, what was it that I learned, in this last week? And if I can't summarize it to myself when I'm away from the book and everything, then I know that my learning was kind of incomplete. And then it's always really startling to me too when I push myself to summarize it. What are the few things that I can list, and what are the things later when I come back that I couldn't list? And what I'm actually doing when I do that is I'm giving myself kind of like a practice quiz. And I remember one time, a number of years ago, I had a student she was in a calculus class, and she was an older student. She was a lawyer. She was going back to school to become a patent attorney. And so she needed more math. And she was really impressed by the amount of learning that happened through her practice quizzes. And one day she came into class and she had dug up this article. And the point of the article was they tested all these different ways to see which way people remembered things the best. And what came out on top was giving people a test. Is when they tested themselves over things, and then they checked. Soon after that, the testing themselves was more effective than just reviewing it and doing all kinds of other kind of things. And so that kind of reinforced the idea of the practice quiz. So the average value, we have y equals x cubed goes from 0, 0 to 2, 8. Right here. And what's the average value? Well, it's always positive. And its low end, it's at 0. And its high end, it's at 8. Its average, then, between the lowest height of 0 and the highest height of 8, I might think that the average would be 4, because that's halfway in between. Do you agree with that reasoning? The average is 4.
No,
No? Why not?
because you have 3 x values instead of just 2. So the average height would be 0 plus 1 plus 8 divided by 3.
Ah, very good. What you're kind of saying is, like when you have 1, when x is 1, you're way down here. You're not at the halfway point right up here. And you could take 3, you could take even more values, but what I'm doing would be valid is if this function had gone along this dotted line. But it didn't, and it hung down low. So my average height should be lower than 4. So let's cross out 4, maybe 3-ish. Does that seem reasonable to everybody? Anybody disagree with that now? All right, we can actually get this average value exactly. And it's a really easy idea. The average exactly is, remember, let's get this area. Let me change to green. I can get this area under the curve. So that area, this is the definition of a definite integral, is made to get areas. X from 0 to 2 of x cubed dx. Now, antiderivative of x cubed is x to the 4th over 4. Excuse me, I'm about to sneeze. There we go. From x equals 0 to x equals 2. When x is 0, that just zeroes out. When x is 2, I get 16 divided by 4, which is 4. Yeah. 2 to the 4th, 16. I get 4. Alright. So, that is not the average value, not the average height of this. It's just the area here. But I can use this area to get this average. Does anybody have an idea how I might do that? How can I use that area to get that average height?
Could you look at it as if it were rectangular, perhaps? Or?
That would be it. If you squashed this area into the shape of a rectangle, the rectangle that had exactly the same area as the green stuff, now it looks a little bit too high when I put it there. I'm going to control and take that off. Looks like I have to put that a little bit lower. The height of the rectangle that would have exactly the same area as the green would tell me the average height. Now, since we know the area of the green is 4, and we know the width of this rectangle is 2, then this height must also be 2. 2 times 2 give me the area of 4. So the average value of f on that interval is going to be the area under the curve divided by the width of the rectangle. And then that would have to give you the height. So we said the area was 4, the width of the rectangle is 2, and then we come up with 2. Now I had estimated 3, but I hadn't realized, oh yeah, this is really down low and going way up. And when I drew my line across, it did make sense to put it lower than 3. I'll put it down more like a 2. Alright, so to see how well you understood this, I have another problem. Number 5. Doing the same thing. Estimate the average value of f of x equals 3x from x equal 1 to x equal 5. So go ahead and do number 5. Now there's actually a couple different ways you could do number 5. And if you can find one of the ways or both, that'd be great. Alright, anybody need more time? Don't hesitate to let me know if you do. Alright, so we're going to draw a picture here. So the x is going to go from 1 to 5, while the y's are going to go from 3, because when you plug in 1 into this, you get 3, all the way up to 15. Alright, now I can find the average value of this one without using calculus because it's a straight line. The average value of f is halfway between the height of 3, which is its lowest, and the height of 15, which is its highest. So the average value of f is 3 plus 15 divided by 2, 18 over 2, which is 9. Halfway in between is 9. That's the average value. Now, on the problem we did prior to this, no such shortcut was available. That only works and gives you the real answer if it was a straight line. Now, we want to be able to do problems like this where we don't have linear and the only way to do it is calculus. So I'm going to do this via the calculus method. The other way that we could get this is, let's get the area of the region between here and there. I can get the area by the integral from 1 to 5 of the function 3x dx. Now actually I don't even need to do this with calculus, but I really want to illustrate the calculus. That's the whole point of this. The area could also have been done by, you use the average height, 9, times its width, which is 4. 9 times 4 is 36. Now, I should be getting 36 here. The integral of 3x, the 3 comes out front, you get x squared over 2. I'm going to put both constants out front. I'm going to put x equal 1 to 5. And then that's going to be 25 minus 1. So it's 3 halves times 24. This goes into this 12 times, and that's equal to 36. Exactly what I knew it had to be, because the average height times the width of 4 is 36. Okay, so that's my area. Now if I was continuing to do this, the average is always going to be if it's a region above, strictly above the x-axis, but we're going to find out that it works all the time, even if it's below or anywhere. The f average is the area under the curve divided by the width of the rectangle. So the area was 36. The width was 5 minus 1. Alright, so that what that means is if we stuffed this area into this rectangle, what does its height have to be? And that turns out to be 9, like this. So that's average value. And give me a little feedback on average value. Is it too fast to really get it, or you think you got it? Okay, so this idea of average value of a function is because we had an unscheduled day of review last time, we are going to have to skip a section, and then we're going to be skipping section 5.4, and in 5.4 there's multiple topics. But the only one that I think is really important is this average value of the function. So we're going to be skipping 5.4, but I'll assign just a few problems with the average value of f in 5.4 so that you can practice this idea some more. And this idea of the average value of a function is something I use all the time when I take an integral. Let me come back to this one over here. If I was asked to take this integral from 0 to 2 of x cubed dx, I usually never do these steps directly. Usually what I do first is I estimate this. How do I estimate it? I draw a quick rough sketch like this, and I tell myself, alright, I'm looking for this green area under the curve. that green area is going to be, and then I say the width of the rectangle. If I squashed all this green area down into a rectangle, the width is 2, and the average height would be about, and then I estimate the average height, and I'd say, oh yeah, it looks like about 2. Maybe I would have guessed 3, like I did guess. And then I would say, all right, the 2 times the 3 is 6, and I'd say, oh, roughly it's going to be about 6. And then, only then do I actually work it out and get a number. But the advantage of doing it my way is always estimating it first and always using the average height to help me estimate the area of the region is when I make an error, it immediately shows up as something unreasonable. Like if I estimated the area was 6 and I did the integral and I got a negative number, I would say, hey, this doesn't jive. I know it had to be something positive. Or if I got something way different than 6, like 500, oh, I must have punched something into my calculator wrong or done some step wrong. I always get an estimate first, and then I do the calculus, and then I have some reference to see if my answer is reasonable or not. And so I actually don't compute the area, the average values. I use the average value in the opposite way. Because watch, see this equation right here? How I'm really using it is in this method. These two multiplied together equal the same as these two multiplied together. The area is the average height of the function times the width of the rectangle. And I can easily estimate an average height by just looking at a function. Sometimes I don't even draw the function. I just plug this in, use the left endpoint, use the right endpoint, 2 and 8, take the average of those 2 points. So that way I'm kind of like using the line segment between them and using the midpoint. The average height is along that line segment, but usually that's all I need it for is an approximation, so oftentimes that's fine. And then I use that. Alright, now let's go to number 6. 6 is a crazily worded question on purpose. See if you can make sense of this and give an answer. How much area does the function f of x equal x squared accumulate above the x-axis from x equals 0 to x equal x? Okay, let me stop you. So I'm this is just the right half of this parabola. How much area does that function accumulate above the x-axis when x is something like here and then moving out to the right? It's kind of as the x moves to the right, we accumulate more and more area. Well, the answer is, how much area? It's an area function. It's the antiderivative of this one. And let me know if you're able to get that before me, or if this just didn't make sense, or where are you at with this one. It's kind of putting some things together. All right, that's it for the practice quiz. So, questions on homework. I think there might not be many, because last time I think we had the review day and we got probably most of them. But is there anything else that somebody still needs, that's burning, that they need to ask about?
Yeah.
Okay.
Let me just look at my homework. So,
Mm-hmm.
for number, oh wait, no, I think I got that one. Oh yeah, number 49. I don't really understand
Is this
when
in
you have,
5.3?
oh no, I'm sorry. This is the review. I'm sorry.
The
I thought
review
we
for the
already went over 5.3.
Okay, yes. So it's a review for the final?
Yes,
So which section is it then?
it's 1.3.
Section 1.3. Problem number 49. So this one here?
Yes.
Okay. I'm glad you're working on the review. All right. And do you have a specific question on this, or do you want me to just start from scratch, or how would you like this, Kylie?
I'm just wondering because it says assume a log of b of x blah 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 equals these numbers. But when you have a square root, does that mean you just, I tried figuring it out myself and I couldn't figure it out, even using the properties of log.
Okay.
And I kept getting a different answer from the book.
All right. Let me show you this much of it. If we just isolate this part, log base b of the square root of x. Now, I know this is true. So is this equal to the square root of 0.36? This would be my first instinct on this, but it's not true. That would be true if the square root had been like this. That one is this, because then you can substitute log base 3 of x as just 0.36. Alright, so if that's the case, then how in the world am I going to do log base b of square root of x? I can't just square root that thing over here. I'm going to have to use some properties of logarithms. And one of the properties is...
Oh, that's right. Now I remember.
Yes,
Yeah.
okay.
That's the third property rule.
This gets to come out front. And then the log base b of x being 0.36 can get substituted right in here. Okay, so that, it doesn't take the square root of this, it just takes the 1/2 of that, because of the way the logarithms work. And so there's more complicated parts to that, but that's just isolating that part. So is that enough to get you going there, Kylie? We'll just do that much.
Thank you.
You're welcome. All right, any other burning questions? $71 from 5.3. All right. Oh, 5.3 is already here. Find this area of the region. All right. So the one that we did over here was 49. And now over here, we're looking at 71. And now find area of the region, bounded by the x-axis and the function. That's the definition of the definite integral. The area we're looking for is the integral from negative pi over 4 to 3 pi over 4 of sine of x dx. So the very definition of the definite integral, it was created to find areas between the curve and the x-axis. All right, now this one I'm going to do it as an example of how I do integrals. I don't just do them, I estimate first. And I'm going to draw a quick picture. And I'm going to go from negative pi over 4 to, so here's 1/4 pi, 2/4 pi, 3/4 pi. Okay. And the sine function, so this is, let me label a couple more. The sine function, every quarter of pi changes like this. No, every, I have it backwards. Didn't do that. Every half a pi it does that. Pi over 2, it goes up to here. Pi, it would go down to here. 1.5 pi would be over to here. So on. Hold it. No. Pi over 2. Well, pi would be to here. And then, so let me just graph this real quick. Pi would go there, and then it would go down, and it would go back up. this doesn't reach its low point yet. It's still got to go further to get to its low point. So, kind of screwed up a little bit. Okay. Now, we're going to be finding the area. This is going to count as negative area. This is going to be counting as positive area. And I'm going to definitely have more positive area than negative area. And then the width of this whole thing is pi. Pi times, now the average height might be, I don't know, 1/3 or something like this. So I'm going to estimate area is 1/3 times pi, average height, times the width of the rectangle. Average height, I'd say maybe it's 1/3, and then the width from negative pi over 4 to 3 pi over 4 is definitely pi. So I'm going to guess something like pi over 3, which is about 1. Pi is barely larger than 3. So 1 is my rough estimate. Now I'm going to work this out. And the antiderivative sign, a function whose derivative is sine, is negative cosine. Okay, so I factored out that negative. When I put 3 pi over 4, I get cosine of 3 pi over 4 minus cosine of negative pi over 4. Now, I'm going to draw my little tiny unit circle. 3 pi over 4 is over here. The cosine of that is the x-coordinate of that point, which is negative square root of 2 over 2. Minus, now I'm going to have this point right here, because that's negative pi over 4. And the cosine of that is positive square root of 2 over 2. And then this is going to equal negative, and then these two have a common denominator. The 2's will cancel, the negatives will cancel, and I'll just get square root of 2. It's positive. What had my estimate been? 1. And I got, and the square root of 2 is about 1.4. That's in the ballpark. So I'm happy with that answer right there. Any questions on 71? How it worked out?
Mr. Shankin,
Yes.
the answer is 2 in the back of the book.
It's positive 2?
Yeah.
Okay. I could have made an error.
I don't think you made an error. I think that's another thing I was going to ask too, is that I think they want us to take the absolute value. And I'm just wondering, when do we do that versus because what you did is what I originally did, but then when I did the absolute value, I got 2. And splitting it up in...
It has to do with their instructions. All right. The directions, I'm looking at it in my textbook now too. 67, find the area of the region bounded by... And how do they ask? Find the... okay. All right, I think they could have been clearer on their directions. I don't find this clear enough. If what they really meant for you to do is to interpret this as positive area. I think they should have stated that as well. Find the area of the region, and if it goes below the x-axis, consider that as a positive area. Because the definition of the definite integral is kind of loosely saying this. It's the area of the region, but you have to count regions below the x-axis as negative. All right, so we'd have had to get the answer that they want is you have to take two separate integrals, the integral from negative pi over 4 to 0, and then stick an extra negative with that to turn it into a positive, and then from 0 to 3 pi over 4. And if you do that, you get the answer. So that must have been how they wanted it to be interpreted.
I was wondering, were they just asking for the bounded range for the cosine? Like if you restrict the domain of cosine, maybe that's what it was asking?
I don't think so.
No?
I think it's really trying to get you to get these two areas, but I'm pretty sure it's this area right here as positive. Okay, and how you give answers in that region, I'm not going to check those, and I'll be more clear when I ask such questions, like on a test or something. Okay, that takes us to our break point, so we'll stop here, and we'll start with the new section 5.5 when we get back. So we'll start again. At 12:49 p.m. See you in a bit. All right, we will start up again, and we're going to do 5.5, the substitution rule. And we're going to be taking the derivatives of, or taking the integral of more complicated things today. We're going to start with number 1, derivatives, because I need to show you an analogy. Power rule, example. If I take the derivative of x to the 7th, I get 7x to the 6th. More complex. Example. If I take the derivative of 3x minus 5 to the 7th. So it's a function within the outer function of raising to the 7th power, a function within a function. We can only do this one because we have the chain rule. So 7 times 1 is 7, decrease the exponent by 1, and then multiply by the 3, and that comes in there because of the chain rule. Alright. So when x gets replaced by a function of x, it's not a problem for the derivative. We handle it through the chain rule. Okay. Function of function, derivative of a function of a function, no problem. Because the chain rule bails us out. Now let's go to number 2, integration. Power rule, example. The integral of x to the 5th dx. Well, that's just x to the 6th over 6 plus a constant. More complex. Example. Suppose I do the integral of 2x plus 8 to the 5th dx. Now, I am going to ask a question here. Is this going to be 2x plus 5 to the 6th over 6 plus a constant? I'm going to do it pretty much the same way I did this. Raise the power by 1, divided by 6 plus a constant. So, I'm going to have you consult in your group for a minute, and then I'm going to call on a group and tell me if you think this is going to work. Hopefully that's enough time. Let me ask group 4. Do you think that'll work? Yes or no?
No,
Why not?
because it doesn't take the inside function's derivative.
Very good. We can actually check our work. Check by differentiating both sides. When you take the derivative of this, you got to get this. When we take the derivative of this, we got to get this. When you take the derivative of that, d dx, the 6's cancel. You get 2x plus 5 to the 5th. But you got to take the derivative of the internal function, which is 2, and that doesn't match. Oh, this was an 8. My 8 turned into 5, so let me fix all those. This doesn't match this because of that extra 2 right here. And the problem. There is no chain rule for integration. But somehow we have to account for the chain rule with this extra 2. And if somehow we could account for that 2, we could kind of get this thing to work. If we just, either multiplied or divided this thing by 2, I bet you we'd have the right answer. So how do we do that? The solution is we're going to use what's called a U substitution. And the U substitution is going to solve this problem for us. It's going to have some limitations, some really big limitations. So it's not going to be as good as the chain rule, but it'll allow us to do a bunch of integrals that we couldn't do before. So let me put this into the notes. Let's keep going. So let's summarize what we've, and kind of generalize what we have learned so far. In summary, if I take the derivative of f of x to the nth power, I get n f of x to the n minus 1th power times f prime of x. And that f prime of x was the chain rule. Furthermore, if I have the integral of a function of x to the nth dx, we can't do it. But we can do this integral. If I have an f prime of x there, I'll be able to do it. But if that f prime isn't there, because notice, how have we always made integration rules? We integrate both sides of a derivative rule. And if you have a function to a power, you also need that prime there. This will just be a constant, and we can adjust for this constant to make it, n instead of n minus 1. The constants won't be a problem, but when we integrate both sides, we'll need both parts of this to be able to do this. We will do this by doing a u substitution. We'll create a new letter u, and we'll let u be f of x. Then du dx will be f prime of x. So, and here we're going to do something that we've never done before. We're going to treat the du and the dx separately. And I'm going to multiply both sides by dx. du equals f prime of x dx. Now this was part of Leibniz notation. He said, hey, it'll work like a fraction. Treat it. Have a notation that uses and takes advantage of that fractional thing. du dx. All right. Now, when you get further in math, like after the calculus sequence, Calc 1, 2, 3, a very common class after that is called differential equations. And in a differential equations class, you often see these letters split up like this. du over here and dx is over here. And then they often, textbooks don't really often explain what these mean when they're separated out like this over here. And so, just in case you keep going in math, I'm going to give you a quick description here of these du's and the dx's, what it means when you pull them apart like this. So, remember the interpretation of du dx is change in u every time the x increases by 1, provided we stay in a tangent line. It's the instantaneous slope. We could also imagine that dx is a really, really, really tiny change in the x. Like if the current value of x is 100, dx might be 1/1000th. A really, really, really tiny change in x. And that will cause a little change in the u to happen. And for instance, if du dx is equal to 5, then when dx changes by 1/1000th, u will change by 5/1000th. The ratio of that will become constant as we get really, really close to the value we're interpreting it. All right. So when we split them up like this, we can still kind of think of them that way, but it's kind of hard to think of that way, because you might think of this as an infinitely small change in u, an infinitely small change in x. And this used to be the way that mathematics, calculus, was taught many years ago. And with these things, and they called them infinitesimals. And this thing was infinitely small, but not 0. And this was infinitely small, but not 0. And it was really difficult for new students to figure out, what in the world does this mean? How do you mean this infinitely small thing that's positive but not 0, and yet it's in, and the thing is this can get really, really small, this can get really, really small, but the ratio of those two stays the same and becomes your derivative. And But anyway, this, we're going to treat it more like it was just an algebraic manipulation. We multiply both sides by dx. We're not going to get stuck on that interpretation that these are infinitely small. We're just going to wind up using this kind of notation here. So then we're going to wind up going back to this problem, and we're going to rewrite it all in terms of u's. So then, when you have all this available to you, this becomes a new integral. U, it's replacing the f of x, u to the n, and then f prime of x dx all gets replaced by du. And this is something that's just the power rule. That's u to the n plus 1 over n plus 1 plus a constant, and we'll get an answer. So this is the theoretical side. Usually I do something really practical first, and then I show you the theory, but I'm flipping it around here. I want you to see the theoretical side of what's going to happen with our u substitution, and then we'll do an example. Alright, so the u substitution will allow us to rewrite this nice and simply, and it'll force us. What it really is going to do is going to force this. If you can't get it so that this is like this, then you probably had a problem like this, and you just can't do it. But if you can do it with the u substitution, we'll be able to get our answer. Alright, so let's do this problem now that we were looking at. Let me put this into the notes. Example 1. The same integral we were looking at before. 2x plus 5 to the 5th. And we found the wrong answer, which was identified as wrong and because it didn't have that extra 2 accounted for. Alright. How I'm going to account for that 2 is with this u substitution. So, before I start on this problem, I notice if this had been x to the 5th dx, piece of cake, it's just x to the 6th over 6 plus a constant. But since it's a function of x to the 5th, I can't treat it like it was this and just write 2x plus 5 to the 6th over 6 plus a constant, because that's what we just identified gives us the wrong answer. So what I'm going to do here is let u equal 2x plus 5. Then du dx, the derivative of the right hand side is just 2. Then I'm going to multiply both sides by dx. du equals 2 dx. Now, you'll be doing enough of these that after a while you'll be able to go right from here to here and kind of skip over this. But at first, we'll just write it out so it looks familiar when we get this. Alright, now once you get this to this point, the technique I use is I come back to the original problem. I know that this is going to be replaced as u to the 5th. And then everything else that's there, I want to match exactly that down here. So I'm going to divide both sides by 2. 1/2 du is equal to dx. So I get this to exactly match this. Now, once I have this, I can rewrite this problem without using any x's. How can I rewrite it without x's at all? Well, 2x plus 5 to the 5th becomes u to the 5th. dx is 1/2 du. And now we've changed this from a function of a function into something that's just the same variable to a power and then that du. So I don't need to, I can do this one. This 1/2 gets to come out front. And from now on, when I go from here to here, any constants will automatically I'll just put out in front. So I don't have to do 2 steps here. And then this becomes 1/2. The integral of u to the 5th is u to the 6th over 6 plus a constant. The moment you get rid of your last integral sign, you have to put a plus c. This is 1/12 u to the 6th plus c. Now I'm done, except I can't leave my answer in this format. The original problem didn't have u's in it. It had x's. So I have to reverse my substitution, go back to here, replace the u with 2x plus 5, and I'm done. Now when I did it before, I didn't have the right answer, because I didn't account for the chain rule that we got an extra 2. When I do it now, I can check my work. If I take the derivative of this, the 6 and 1/12 multiply together to become 1/2. Chain rule, 2, and then the 2 and the 1/2 cancel each other out. And this matches exactly what it's supposed to. It checks. Alright, there was a lot in this for a u substitution problem. There's no chain rule for integrals. So we get around that by doing this u substitution, which will force us to make sure it's the right format. And we'll correct, for instance, this one. I knew when I was done with my other problem that it was off by a multiple of 2, but I couldn't really tell without thinking hard about it whether I multiply by 2 or divide by 2 to redo it. Well, this one just forces it correct. Alright, let's take a picture of this. And let me have you do one of these, and then we'll generalize it, because we get even more generalized than this, and we get some pretty tricky problems in this section. going to give you, this is example 2, but you're going to work on it. So find the integral, 7x plus 3 to the 4th dx. Let me give you a minute. Get going and get as far as you can on that. I'm going to interrupt you before you finish, probably. But get as far as you can in the next minute. Alright, so I'm going to create this new variable u to be the inner function. Du dx is 7, multiply both sides by dx. Now I want to match this thing exactly, so I'm going to divide both sides by 7. So now I can rewrite the whole problem without using any x's. U to the 4th. Instead of dx, I'm going to put 1/7, but I'm going to put that out in front. Du. This is 1/7 u to the 5th over 5 plus a constant, which is 1/35th, and then u to the 5th is 7x plus 3 to the 5th plus a constant c. Alright, give me a little feedback on how you're doing with this so far. Is it going too fast? Or are you okay with this, what we got? Let me take a picture of this. Kylie, you think you found a shortcut?
Yeah. So I've noticed that the constant of the function x with the exponent
Yeah.
will equal the fraction in front of the f of x. Well, plus 1, of course.
Okay.
So if you add 1 to n for the exponent and then
Yes.
multiply it by the constant, you get the fraction.
You get the fraction up front. Very good. Good observation. And you can take advantage of that if you want, but that's actually going to be the smaller amount of the problems. The majority of the problems are going to get significantly more complicated than this. And we're going to generalize our abstract rule even more. The integral of g of f of x dx, we're going to say that we can't do it. The integral of g of f of x with an f prime of x dx, we will let u equal f of x, du will wind up equaling f prime of x dx. We'd really get du dx and then multiply both sides by dx. So we get f prime of x dx, like this. And then this becomes the integral of g of u du. And we can integrate if we can integrate g. Sometimes the function g we don't know how to take the integral of. Like for instance, remember the integral of secant squared? We can do that. But the integral of secant, we can't. It has to be the output of a, for a trig function, it has to be the output of a derivative. Okay. So, let's look at some more examples in this context now. So, example 3. The integral of x squared, x cubed plus 1 to the 8th dx. I like that idea of looking for shortcuts right away though. I'm constantly doing that same thing too. Alright, on this one. We are going to need to do a u substitution here. And we're going to need to let the u be either x cubed plus 1 or have it be x squared. And take, well, let me just ask this to anybody because I got to move kind of efficiently here. Anybody, which one should I let be my u? The bottom thing or the top thing?
The bottom.
Okay. And let's try it for just the top thing for just a second. Let u equal this. Du dx would be 2x. Du equals 2x dx. If you choose your u to be the wrong thing, what you will find is when you come back to here and you say, well, we were doing it like this. When you rewrite it, you'll have a hard time not using x's. You'll get a u on the top, and then the rest of it will be, how do I fill it in? I gotta have that, and you'll wind up having a big problem. Okay. And let me take a picture. To it now. So, especially when you're first starting, there's going to be trial and error in these things. Don't expect you're always going to get the right answer each time with this U substitution thing. You might have times you pick something and it doesn't work, and then you gotta go back again at it. So if we take it as the bottom, now here I just made another common student mistake. You don't take it to be the exponent, the 8 as well. It's just the inner function, and when you have two of them like this, it's the inner function of one of them, not the other. Okay. Now, let's do du dx. The derivative of 1 goes away. I'm going to get 3x squared. So I'm going to get, when I multiply both sides by dx, 3x squared dx. Now, notice, can I write this without using any x's now? Well, the bottom is just u to the 8th. And everything else that's left, x squared dx, is right here if I divide by 3. And I have this matching with that. So the x squared dx becomes 1/3 du. And I'm putting my 1/3 out in front. Alright, now, let's compare this, what we just did, with this general format up here up top. Let me wait a moment to let people catch up in case they're taking notes.
Mr. Shankin,
Yes.
could you, I mean, like for me, when I see it, I guess what I was looking for was to see if I could spot a function's derivative. Is that like a way to do it? Like if you look at like in this case, a rational function, if you see one and you can kind of spot something similar to its derivative, like can that be
That is exactly the way we're going to look at it. Good anticipation. So, comparing this to over here, we're looking for two, notice, in order, you can't do it if it's in this format. The only ones we can do is if there's an inner function and its derivative with a dx that exists. So what we start looking for now, as we get more sophisticated in this, is we look in here for two different functions of x. And notice I see this function of x is 1 degree higher than this function of x. So the derivative of this one is going to give me this one right here. That's got to be the relationship here for this to work. It turns out that where we can take the derivative of almost anything, we can take the integral of only very special ones. If this, instead of a 2 as the exponent on the top, if this had been a 7 power, we would not have been able to take this integral. The only reason why we can do this was because the derivative of this function gave me this function exactly. I had to have this be a 2 right here. Because there has to be two functions of x where one of them is the derivative of the other. And the one that's the derivative of the other has to wind up being the numerator function as well, because it and the dx will combine to become the du down here. So all of this happens, and I get 1/3 integral of u to the negative 8 du. Now it's the power rule. 1/3 u to the negative 8 over, no, add 1, negative 7 over negative 7 plus a constant. This is negative 1 over 21, u to the negative 7 plus a constant, negative 1 over 21. Some come back, x cubed plus 1 to the negative 7 plus a constant. This is my final answer. I took the antiderivative of this and I got this. And if I check my work, now I'm running out of time here, so I'm just going to check my work without writing it down. If I take the derivative of this, negative 7 to negative 120 reduces to positive 1/3. This to the negative 8. Chain rule, and I get times 3x squared. And the 3x squared would give me the x squared, and the 3 and the 1/3 kill each other off, and we get the derivative of this is this thing right here. Let me take a picture. So we're getting more and more complex very quickly. This is our general thing. We started off with the g function just being something to the nth power. But then the g could be anything. And then we can take these integrals. Let's do another example. Let me find this. All right. By the way, this section, was that example 3? I think so. I think we're on example 4.
Yes.
By the way, this section is it's one of the kind of how do I describe it? For some students, it takes a long time for them to really get the hang of how to do these problems. So don't think that you're going to pop this section out in a quick hour or so. It's a little bit different way of thinking. You got it, but it's actually a really important section though, because this sets the table for Calculus 2. We wind up doing this kind of thing all the time in Calculus 2. All right, so example 4, I'm not going to do these problems, I'm just going to show you something. The integral of x squared plus 5 dx, we can't do it. While the integral of x squared plus 5x dx, we can do. How come I can't do this one, but I could do this one? Well, we compare it up here. I need an f and an f prime in here. And if the f is x squared plus 5, there's no f prime which would involve an x. So I just can't do this one. Well, hold it. I'd have to have a power on this. Otherwise I could do it. Okay. This one, here's my f, here's my f prime. Now the f prime is off by a constant, and that's all you're allowed to be off by a multiplicative constant. And then you can account for that. And this one we can do, this one we can't. And if you look at this one in this manner, of all the exponents I could put on that, I have to put the exponent of 1. It's the only one I'm able to do. If I make that exponent any other number, I cannot do this integral. Let's go to example 5. I'm going to demonstrate two things with this one. The integral from 0 to pi, because the one thing I'm demonstrating here is that it's a definite integral. So it's our first one with a definite integral. Sine to the 5th theta cosine theta d theta. Okay. So what I'm going to do for this one is I need to, generally your first step on each of these problems is to pick the right u. Well, let me point out, if the problem had been this, we can't do it. Because there's not two functions of theta where one is the derivative of the other. Can't do it. But this one, we can do it. Now I have two choices. I can let u be cosine of theta, or I could let u be sine of theta. And when you're first starting out, it can be confusing. Just take a stab at one of them and then see what happens. If you did this, you'd run into a problem. Du d theta would be negative sine of theta. The negative is not the problem, because that's just a constant. But you would wind up having the du you see that you need this thing fifth powered, but you can't have the theta fifth powered. And the only way you can have this on fifth is the fifth power both sides, but then you're going to have du, we can't do that. The du has to be not raised to a power. So you try things, and you go back to the drawing board, and you say, all right, that wasn't the right u. Let's try the u being. So I need two functions where one's the derivative of the other for the format. Now, du d theta, derivative of sine is cosine theta. So du is equal to cosine theta d theta. All right, now, I'm fortunate in one aspect. This, when I rewrite this without thetas and with only u's, that's going to be u to the 5th. Everything else already matches. I don't even have to divide both sides by a constant. So this becomes. Now, before I put the rest down, I'm going to go back and I'm going to put, and this is what I'm going to recommend you do as well, whatever the variable is in here, write these out right here. Theta is 0 to theta is equal to pi. When we change, we're not going to be able to write thetas anymore. Everything has got to be u's. This becomes u to the 5th. Cosine theta d theta becomes du. And here is a very common student mistake. They continue to put 0 and pi. But if they put 0 and pi, you see what the problem would be? They'd still be using thetas. And you can't mix thetas with u's. So, what we do is when you change everything to u's, also change these as well. And it's not as difficult as it seems. How do we change to u's? By looking at this equation right here. So, when theta is 0, u is going to be the sine of 0. When theta is pi, u is going to be the sine of pi. Just look at the u equation. Now, we know what the sine of 0 is. Quick unit circle. The sine is the y-coordinate at that point. So this is 0. Sine of pi, the y-coordinate at that point is 0. Now, I have 0 to 0. I don't need to bother doing the rest of this. The integral from 0 to 0 of any function is going to be 0, and I can be done. But, let me keep going. Suppose you hadn't noticed that. You would have gone u to the 6 over 6. But I'm going to put out the 1/6 out in front. Evaluated from u equals 0 to u equals 0. And then you get 1/6 when you put in the upper one, you get 0 to the 6. When you put the lower one, you get 0 to the 6th. And then 1/6 times 0 is 0, and that's my answer. And we can do definite integrals. This is what I showed you was the efficient way to do it, is change these endpoints. There is another way to do it, which is very inefficient, which is you send the u's back to thetas, and then you plug back these points in, and you'll get the same answer in the end. But it just goes quicker if we just change these limit points here to here. All right. Questions? I am going to guess that there's a lot of you now that feel like, holy cow, this was pretty tough, pretty abstract. And it is. It's very doable, but it's might take a little time to get used to what's going on and how these things up here relate over into here to do all these with the u substitution. Again, I'm going to anticipate the homework might be a stiff learning curve to, like, as soon as you get to one of the more tough ones, like really having a hard time. But then once you get a hold of the idea, then maybe a whole bunch of the problems will kind of go a fair amount quicker. Okay, any questions or comments? I put a post, an announcement that I had over the weekend. I went and looked at all assignments. I'm trying to give 10s on every assignment, but some assignments like just had 1 or 2 problems I needed to redo, or a few problems to finish, and I had put comments and I had not graded them. And people had all semester to change those, and if they hadn't changed those by this weekend, I put a 0. But you can still make those changes and still get credit for that homework right up until the final exam, which is this Thursday at 11:30. But after that, I won't accept any of those changes. So if you have outstanding work, check if you've got something that's a 0. You can get that grade up. All right, if there's no questions, we will stop here. And let me stop the video. And if anybody wants to ask an individual question, you can just hang on for a while. I'll hang out here.